a statistic we use to analyze or summarize qualitative data. And that's not what this section is about, but here it is. The variable that we use is p with a little hat on top of it. We call it p hat. It's known as the sample proportion, also known as the relative frequency. So all of those relative frequencies that we've been calculating, those have all been proportions, except we haven't been using qualitative data, and closely related to a percent. So as an example, if we have 20 students in a class and 5 of them are from Midland County, we would have n is equal to 20 and x is equal to 5. I didn't give you the formula up here. This is x divided by n. So x is a frequency of the class, and the n is the sample size. You take we didn't call it a sample proportion, we called it a relative frequency. But you take the x and divide by n, 5 divided by 20, and you get 0.25 that you can convert to a percentage when you interpret what the proportion means. So we would say 25% of the students in the class are from Midland County. But that's really the only statistic that we have that is related to qualitative data. Section 3.1 and 3.2 and much of what we do in Chapter 3 and Chapter 4 will be focused on quantitative data. One of the things that we always like to know in a data set is what is the middle? What is the center? You know, if you have a data set where you have some large data values and some medium-sized data values and some smaller ones, well, what comes in the middle? If we know what's in the middle, then we kind of have a sense of what the other data values are. This is a section on the measures of center, and they are mean, median, mode, although mode is something that we use more often for qualitative data, and the last one is mid-range. We use Greek letters if we're going to be talking about, see, we did some work in Chapter 1 about identifying something as a sample or something as a population. So you need to know, because if you have the whole population, then this is what the calculation of mean would be. And if you have a sample, then the most common use of you're very familiar with, of the mean, is how to calculate your average, say, test score. And what you would do if you had 4 exams, for example, is you would add up all those 4 scores, get the sum, and then divide by the number of scores. And that's what this is saying. So you take the first score plus the second score plus the third score plus the fourth score. You'd stop there because there's only 4. And then you divide by the number of tests. And these two formulas, if you notice, are identical to one another. It's the only difference is that one's a sample and one's a population. We use Greek letters for population parameters. And this one kind of looks like a U, but we pronounce it mu. And here is our symbol for the sample mean. And we describe this one, or say this one, as X bar. You'll find in this course that, you know, we don't just use X and Y's. Every different variable has a different character that we use for it. Let's go down to the example, the mean. Exam time. The following data represent the amount of time in minutes of a random sample of 8 students. Random sample, 8 students. So that gives us the sample size of 8. How long it took them to complete the online portion of an exam in a stats course. And it says calculate the mean, median, and mode. We might as well even include in there the mid-range. All right, so the mean would be to add up these 8 numbers and then divide by 8. You can imagine, you know, what calculating this by hand would be like if we had a data set of like 700 data values. It would just be a mess. And so that's why we use technology a lot of time to do this. Anybody calculate that? Unless I made a mistake, which is very easy to do. This looks like 93.1, just over an hour and a half, because this is in minutes. So this tells us then we know some students scored above 93.1 in minutes, and not scored, but spent more than 93.1 minutes. And half of the students, not half, but some scored less. Some used less than 93.1 minutes. So that's the arithmetic average. These numbers are a little messier than just say whole number exam scores, but you use the same idea. Arithmetic average, that's the mean. So we're going to calculate all of these by hand, and then we're going to go back and use the calculator to show you how the calculator displays these numbers as well. The median is the middle data value. Here's a definition. The median of a variable is the value that lies in the middle of the data when arranged in ascending order. So you must sort the list. So if you have an odd number of data values, then the median is the middle one, because there will only be one middle data values. If you have an even number of data values, then the median will be the average of the middle two data values. Because you're not going to find one in the middle, you're going to get two. They give you a little bit more detail here that tells you what position the median would be in. I'll show you how this works. But just by inspection, let's take, for our example, let's list them from the smallest data value to the largest data value. And then let's pick out the middle one. All right, so 60.5 comes first. And then you have 78.9, and then a bunch of 80s, 84.6, 85.9, 89.9. We've got a 90, 94.7, and then a 122.3, and then a 128.0. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. So which data value is directly in the middle? That data value is called the median. We have 4 here and 4 here. Oops, just there are 8 and 4 there. So here's the middle. There is no middle data value because we have an even number of data values. And so what we do is we take the average of these two. So the median is going to be equal to, now take the average, find the number right in the middle, which is also the average, same thing. We're going to add the two numbers and divide by 2. So I think I can do this without the calculator. 87.9. So we say the median is 87.9. And notice it's fairly close to the 93.1. And that's great because all of these measures are measures of center, so we hope that they're very close to one another. All right, let me just go through this definition just so you have an example and you know what it means. And we're down here because of the number of observations is even. All right, so we do know that n is equal to 8. We have 8 data values. The median is the mean of the two middle observations in the data set. So we kind of said it in words. That is, the median is the mean of the observations that lie in position 8/2 and position 8/2 plus 1, 4th and 5th data values. So that's why down here, here's the 4th data value and here's the 5th data value. So it's like the average, the arithmetic average, the midpoint, the number right in between those two middle data values. The next measure of center is the mode. And again, usually we use the mode to identify the most popular, most frequently occurring category. And, but sometimes a mode is appropriate if you have a lot of data values in a set. But it's defined to be right here. And the mode is the most frequent observation. So here are our observations down here for our example. Which one occurs more than the others? Another way to say that, is there a data value that occurs more often than any other data value? Does 60.5 occur more than once? No, just once. All of these data values appear exactly one time. There is no data value that appears more often than another. And when that happens, we say that there is no mode. There is no data value that appears. I mean, our options are to say that, you know, every data value is a mode because they all appear the most number of times. But what we choose to say instead is that the mode is the data value that occurs most frequently, but it has to occur frequently than some other data value. And all of these data values occur with the same frequency. So no mode. So mode is not useful here. And the final way to identify the center of a data set is to use this 4th statistic, which is the mid-range. And you're just going to take the maximum data value and add that to the minimum data value. And if you think about it, the max and the min, right in between, the distance between the max and the min is called the range. And so right directly in the middle is what we call the mid-range. So you're taking the mean of the max and the min, or the arithmetic average between the max and the min. You add the max and min, divide by 2. So in our example, down here is the min, and the largest data value is the max there. So we take the max, 128.0, and add that to the min, 60.5, divide by 2, to put us directly in the middle of the range. And when we calculate that, 94.25. All right, so here are our answers. They all represent the measure of the center, so they all should be fairly close. Although if you've got a data set that's widely skewed, they're not going to be the same. And in this case, we didn't have a mode. All right, now go ahead and get your calculator out, because most of this course, our data sets are going to be more than eight individual data values. So you're not going to want to calculate these summary statistics, particularly the ones that come in the next section, the standard deviation and the variance. You're not going to want to calculate these by hand. It's just too tedious, very easy to make mistakes. Humans aren't very good at that kind of stuff. So what we're going to do instead is to rely on the calculator. Okay, so when you see raw data like this, numerical data, it's almost always a good idea to enter the data values into your calculator. The calculator is, and probably not going to like to hear this, but it's a better calculator than you are. Because as long as you type in the correct things, the correct data values, it's going to give you the exact answer, the correct answer every single time. Of course, if garbage goes into the list, then garbage is going to come out of your calculator. So that's why we check the data set. All right, so you know the steps, hit the stat key, and then edit. Now, I want to come back to my list 1. So I'm going to clear out list 2, and I'm going to make a copy of list 1 and put it into list 2 so I can use it later. So to clear out this list, one way you can do it is just to hit delete, delete, delete. But another way to do it would be to hit the clear key right here underneath the arrows and then enter. But it's important that you have this list highlighted to do that. Now, if you want to make a copy of a list, highlight the list, and then down here in the input row, write down the list that you'd like to copy. Now, all of our list names appear above the keys. So right above number 1 is L1, right above number 2 is L2, right above number 3 is L3, and so on. We've got 6 different lists, and to get the variable name of those lists, they appear right above the number keys. To access any of the blue keys on your calculator, you have to hit the second key first. So to get L4, you'd have to hit second and then 4. So what I'm doing here is I'm going to make a copy of all these data values in case I want to use them later on. So down in the input row, I'm going to hit the second and then number 1. And when I hit enter, it's going to take all of the data values in L1 and put them into L2. It's saying L2 is all the data values in L1. All right, so I'm going to hit enter now, and notice it just copied them all. If I wanted to do it in L3, make another copy, do the same thing. You can make up to 6 different lists. Now you can actually make more than that. If you want to clear out a list, highlight the list, clear, enter. If you want to clear out L5, highlight L5, clear, and enter. It's a quick way to delete data values in your list. All right, I'm going to clear out L1 because I already have a copy of it in L2. So to do that, I highlighted L1, hit the clear key, and then enter. All right, now in L1, I want to enter in my new data values. So I'm going to enter in these 8, 60.5, 128, 84.6, and so on. So you should find 8 data values in L1 only. All right, so what I'm going to demonstrate now is how to calculate the summary statistics. Now we're talking about mean, median, mode, all the ones that they have, but also the standard deviation and the various other things that we're going to be calculating as well. So we've already entered the data into L1, and we're going to do this one here. And then the second thing we're going to do is to calculate the single variable statistics. To do that, we're going to hit the stat key because that's where we always begin when we want to calculate something. And then we want to go over one menu to the calculate menu. The first menu is for entering and manipulating the data. The second menu is to calculate something. Okay, edit the data, calculate something, and then we're going to use this last menu to do all of our hypothesis tests and confidence intervals later on in the course. But we want to calculate the single variable statistics. What did I write? Yeah, one variable statistics. Like this is capitalized. But other than that, it's option number 1. So in the calculate menu, select option number 1, which is the one variable statistics. And then here's where we're going to get into some differences between our calculator. Many of you have newer calculators that have menus in them. But the very first thing you want is your X list. And so you want to tell it where that list is that you want to analyze. So for me, I just need to know that on my calculator and put it in as the first thing. The next thing is they want a frequency. And so the frequency generally is 1. Each one of the data values in L1. Sometimes we're going to be using frequency lists, but that's not the case in this one. Is there anything else in your menu? Oh, anything else in the menu other than those two? All right, once the menu is complete, hit enter, and it gives you all this stuff. Now, the ones that we've calculated so far, we did mention that the sample mean was X bar. And you can see exactly that that's the character that our calculator uses, and anyone else that does statistics that calculates the sample mean uses that variable X bar. So X bar is 93.1. That's the sample mean. Now, the sample mean and the population mean are the same. It just depends on whether it's the same formula. It depends on whether the data set you're working with is a population or is it a sample. The other one that the calculator will give you is the median. But you don't see it on this first screen, but there's a down arrow. You can see there's n equals 8. It tells you how many data values you entered in. When there's an arrow over here like this, that means there's more stuff down under. So to get to the stuff down under, you want to hit the down arrow here, and it'll go down and give you the rest of the stuff. But one of the things it gives you is the median. So the median is equal to 87.9. And the calculator does not calculate the mode or the mid-range. So those are a couple of statistics that you'll have to calculate using the formulas. Calculator doesn't do it for you. And just to confirm, what we calculated by hand, the sample mean, 93.1, and the median, 87.9. The purpose of this course is for you to understand these statistics and interpret them. It's not to crunch numbers in complicated formulas. So every time we have the opportunity to calculate statistics, we are going to do it with technology, specifically either this calculator or Excel. Remember this data set? Go calculate the mean, median, mode, mid-range of this data set. You already have it, remember, in list L2. Now you might, just kind of reflect on these 40 data values. It would take a long time to type 100 plus 279 plus 147, add all those numbers up, and then divide by 40. And when you're done on your calculator, once you divide by 40 and hit enter, you get that one mean, and that's it, that one summary statistic, and that's it. If you wanted to calculate something else, you'd have to use the same values in some other way. So with the calculator, this is very, very quick and very, very easy to do. You just have to get comfortable with the steps to calculate. So here it is. I'm not going to spend much time on this. Stat, calculate, one variable statistics, exactly what we did before. The only difference is that our X list now, instead of being L1, is going to be L2. The frequency is still 1, and then you hit enter. So you get the mean is 220.775. Scroll down to get the median, 211.5. The mid-range, okay, now the calculator doesn't give us this, but it's very easy to do if you know the formula. You take the minimum data value and add to the maximum data value and then divide by 2. We know the min, we know the max, divide by 2. In fact, the calculator gives you the min and the max. Doesn't even ask you to go and look for them. So what's that, 559 divided by 2, 279.5. And the mode, again, the calculator doesn't give that to you, but what you would have to do is scroll through the list to see if there's a data value that appears more than other data values. Oh, looks like 147 appears twice. 190 appears twice. Are there others? 250, 260, 63, 69. Okay. I'm not really seeing any other duplicates here. But what we do have is we do have 2 data values, 147 and 190, that appear twice, more than the other data values. So in this case, we have 2 data values that are classified as the modes. 2 modes, maybe bimodal, but until we see the distribution, we wouldn't know. They have 2 occurrences each. So even with big, messy calculations, the calculator is instant in calculating those statistics. So you should use your calculator for every single problem. Do not try to crunch numbers by hand. As long as you understand how the formulas work, and as you know, you have to use some other method, not a calculator method, to find the mode in the mid-range. But other than that, these calculations are too messy to do them using an entire piece of paper. So I would say avoid that if you possibly can. Let's say that that Burger King came out with a new sandwich, and the new sandwich was, maybe a, triple Whopper or something like that, and it ended up having 3,000 calories. 3,000 calories. We would call that data value an outlier. It's unusual. It's unlike all those other lunch items that you might get at Burger King and McDonald's. So when you see a data value like this, you have to decide, well, is this true? I mean, is this a real data value or is it an error somehow? And if it really was a correct data value and you calculated the mean, I'd like you to compare the mean here to the mean that we calculated before. And here they are. I want to show you by changing that, if we add one more data value to the list, so instead of 40 sandwiches from Burger King and McDonald's, we had 41. When we calculate the mean, the new mean is 288.56, and the new median is 214. Now look what happened when we added that one outlier. When you add that one outlier, the means change quite dramatically. They changed 68 grams is what happened. So one outlier can really sway the mean of the entire data set. Let me just do mid-range as well. Mid-range would be 2,900. That's 3,000 minus 100. Notice how the mid-range is as well. Dramatically different just by adding one single data value. So we would say that the mean is not very resistant to outliers. If you have one outlier in the group, it's really going to throw off the mean, not only the mean, but also the mid-range. It's going to throw them off. But look at the medians. The median is essentially unchanged, almost identical. The median is very resistant to outliers because you get rid of those very large values on the high side or very extreme values on the low side. So that's what this is trying to say here. A numerical summary of data is said to be resistant if extreme values, like adding 3,000 to a bunch of sandwiches where the max is about 450, very large or very small, relative to the data, do not affect its value substantially. So we would say that the median is resistant. Now, of course, if you have a symmetric distribution, a bell-shaped distribution, the mean and the median and the mode are not going to be change dramatically if you add one more data value close in that range. But here's the relationship between the median and the mean for a data set. We have, well, symmetric, we called it bell-shaped, or you have skewed left and skewed right. It turns out that the mean and the mid-range will always move toward the tail in a skewed distribution, and the median stays relatively fixed in the middle. Now, let's take a look at an example kind of using that idea. Journal costs. You see a histogram here, skewed left, skewed right, bell-shaped. The histogram represents the annual subscription costs for 26 biology journals. The mean subscription cost is $18.46, and the median subscription cost is $11.42. Identify the shape of the distribution, which measure of central tendency better describes the center of the distribution. All right, so this is skewed right. And so therefore, you're going to see the median is going to be to the mean is going to be to the right of the median. Median is where where exactly 50% of the data values are to the left and 50% of the data values are to the right. We have 1846, which is the mean, and we have 1142, which is the median. And so you can see that the mean is a little bit larger than, a little bit to the right of the median. These extreme values over here sway the median toward the tail, or excuse me, these large values over here sway the mean out toward the tail. So we have the shape is skewed right, the measure of central tendency that better describes the center. In a skewed distribution, it's going to be the median that gives you the best measure of center. Okay, so we're going to have to return to section 3.2 because we don't have a whole lot of time, but I do want to say just introduce the statistics. Most of the time we're going to be calculating the range and the standard deviation, and well, the range is an easy calculation, but the standard deviation and variance, we're going to use the calculator to crunch the numbers. Section 3.2 are about measures of dispersion or the spread in the data. Are the data kind of all clumped together, fairly homogeneous data set? Or are the data values widely dispersed, where you have a lot of variation in the data values? We have a number that helps us describe how spread out the data are, and it's called the standard deviation. And you can think of it kind of like the average deviation a data value falls from the mean. So instead of just taking all the data values and calculating the arithmetic average of the data values, it's kind of like we're going to take the arithmetic average of all the deviations from the mean. We have a Greek letter sigma to represent the population standard deviation, and we have the letter S. Our calculator uses SX, and for the population standard deviation, our calculator uses sigma X, but uses the sigma nonetheless. And SX is the sample standard deviation. And what you will find is that the only difference really between the two, and then the formulas are different, instead of dividing by the population size for the population distribution, we're going to divide by one less than the sample size to get the sample standard deviation. And the last thing I want to show you is where you get these numbers on the calculator. And because that's all the time we have for today. But what we will do on Wednesday is look at how you would calculate the standard deviation by hand for very small data sets, just so you can get a sense of what it means and how to interpret it. All right, so it turns out that you can find the standard deviation and well, just the standard deviation in the same way that you found the mean and the median. That is, go to stat and calculate and do one variable statistics of the data value in L1. This was the one example with the time watching school after. Here you can see they're both here. The SX is the sample standard deviation right there. And the sigma X is the population standard deviation. And it's always going to be the case that the sample standard deviation is always going to be larger than the population standard deviation. And the reason for that is that we're dividing by n here and we're dividing by something smaller here. If you divide by a smaller number, the overall statistic is larger.